Hi guys, in this video we shall discuss about the theorems in chapter 1 real numbers, which is also very important for the examination who are they are trying to get 10 points in this maths examination. So let's start this theorem 1.1. Based on these theorems we have already had problems and we have solved it. So after saying these theorems, once you all recall that, going back to the my videos and once recall it after my finishing of these theorems explanations. So let's start. Theorem 1.1, Euclid's division lemma. Given positive integers a and b, there exists a pair of integers q and r satisfying equation a equals to bq plus r. So here Euclid's division lemma we have already discussed in introduction, and we have problems based on this in exercise 1.1. So given positive integers a and b, therefore there are two integers a and b which are positive. It will be in the form of p by q. If it is a rational number, so it should be in the form of p by q, and pair of integers q are satisfying equation a equals to bq plus r, where a and b are positive integers, q and r are pair of integers. So coming to the theorem 1.2, fundamental theorem of arithmetic. Theorem 1.2 is fundamental theorem of arithmetic. Every composite number can be expressed, that is factorized, as a product of primes, and this factorization is unique apart from the order in which the prime factors occurs. We have already had one problem based on this theorem 1.2, that is fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, that is composite number means which have factors more than 1 or 2, and it can be expressed as a product of primes, prime numbers which can be divisible by 1 and with number itself, that is 2, 3, 5, 7, 11, etc. And this factorization is unique apart from the order in which prime factors occurs. This is theorem 1.2. And coming to the theorem 1.3, let x be a rational number whose decimal expansion terminates, then x can be expressed in the form of p by q, where p and q are co-primes, and the prime factorization of q is the form of 2 power n into 5 power m, where n and m are non-negative integers. We have already had a lot of problems based on this theorem 1.3, that is, let x be a rational number. When it is a rational number, it should be in the form of p by q, whose decimal expansion terminates, then x can be expressed in the form of p by q. That is, I already said that rational number means it should be in the form of p by q, where p and q are co-primes, and the prime factorization of q is in the form of 2 power n into 5 power n. We have already had this 2 power m into 5 power m problems a lot in this chapter, where n and m are non-negative integers. Yeah, we have already discussed about this in the before exercises. So coming to the theorem 1.4, let x be equals to p by q be a rational number such that prime factorization of q is in the form of 2 power n into 5 power m, where n and m are non-negative integers, then x has a decimal expansion which terminates. This is similar as theorem 1.3, that is x equals to p by q, that is a rational number, and prime factorization of q is in the form of 2 power n into 5 power n, where n and m are non-negative integers as it is, then x has a decimal expansion which terminates. That means when divided x by number, it has a decimal expansion which terminates. That means it will stop. Terminates means it will stop when a number is divided. That is theorem 1.4. And coming to theorem 1.5, let x equals to p by q be a rational number such that the prime factorization of q is not of the form 2 power n of 5 power m, where n and m are non-negative integers, then x has a decimal expansion which is non-terminating, repeating decimals. This is totally opposite to theorem 1.5, that is x equals to p by q, it will be as a rational number. The prime factorization of q is not in the form of 2 power n into 5 power m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating. Here it is terminates and here it is non-terminate. It will be repeating. It does not have a certain number at which a number is divided. So it is repeating and recurring decimals. This theorem is deadly opposite to theorem 1.4. If you have an idea about this, then you can have idea about theorem 1.5. Coming to the theorem 1.6, let p be a prime number. If p divides a square, where a is a positive integer, then p divides a. We have already discussed this in introduction and have some problems based on this. That is, let p be a prime number. We should think that p is a prime number. If p divides a square, that is some number, suppose 2 square or 4 square, then a is a positive integer. This a should be a positive integer, then p divides a. We have a lot of problems based on this in the before exercises. So as I said, these theorems, if you refer the problems based on this I have said in the before exercises, you can be thorough through this chapter. That's it guys, this is the end of the chapter, and in the next video we shall start a new chapter. Okay, bye friends.